Evet.
Öncelikle tekrardan hoş geldiniz hocam. So we are very excited to have Zeynep Akata with us. She's a professor of computer science within the cluster of excellence machine learning at the University of Tübingen. After completing her PhD at INRIA Rhone-Alpes with Professor Cordelia Schmidt in 2014, she worked as a postdoctoral researcher at the Max Planck Institute for Informatics with Professor Bernd Schiele between the years of 2014 and 17. And she also worked with Professor Trevor Darner between 2016 and 17 at University of California, Berkeley. Before moving to Tübingen in October 2019, she was an assistant professor at the University of Amsterdam with Professor Max Welling between 2017 and 19. After that, she received a Lise Meitner Award for Excellence Woman in Computer Science for Max Planck Society in 2014, a Young Scientist honor from the Werner von Siemens Ring Foundation in 2019. And recently, she got a really prestigious ERC, European Research Council, starting grant in 2019. Her research interests include multimodal learning and explainable AI. And today she will be delivering a talk on compositionality and explainability in visual recognition. So thank you very much, Hocam, for being with us today.
Çok teşekkür ederim tanıtım için. Geçen sene başka bir sunum vermiştim Bilim Akademisi'nin Yapay Öğrenme Yaz Okulu'nda. O sunumu Türkçe vermiştim ve de çok iyi gitmemişti sanki. O yüzden daha rahat olduğum bir şekilde vermeye karar verdim bu sefer. Kusura bakmayın. Ama soruların Türkçe sorulmasında bir sakınca yok. Belki becerebilirsem Türkçe cevaplarım. Olmazsa da İngilizceye geçerim. Öyle düşündüm bu sefer. İzin verdiğiniz için teşekkür ederim.
Biz teşekkür ederiz bizimle beraber olduğunuz için. Sağ olun hocam.
So today I will talk about my research on explainability and compositionality for visual recognition. And we are interested in doing this using minimal supervision, not using so many labels. So what I mean by that is, first, the outline of my talk is as follows. I will first describe how we explain decisions of the deep learning models that we train mostly for classification using class discriminative attributes. And then I will talk about how we model the theory of mind of a conversation partner using these attributes. And then I will talk about compositional zero-shot learning. This is a very recent interest of mine. I don't have so many research output on that, but a couple that I would like to briefly mention. And then I have recently started working on audio and videos, so I would like to touch upon that. I tried to make my talk as different as possible from last year's presentation. So in case there are some attendees who have listened to my talk last year, it's going to be different. And then I will summarize and talk about some future works. Let's start with explaining decisions with attributes. So when we look at large-scale data sets like ImageNet, we see that it has a very long-tailed distribution, which means from some classes, only a few classes, we have many examples available. And these objects are usually common objects that we see around us very often, and we can take pictures of them, and then we can name them very easily. But many of the classes that appear in these large-scale data sets that we use to train our deep models contain only a few examples from most of these classes. And this is mostly because taking pictures of these objects is difficult, because these objects are very rarely found in the nature. And also naming them is very difficult, because we don't know if we are not an expert on that object, then we don't know the names of these objects. But ideally, we would like methods to be able to identify many more classes than maybe even humans are capable of. Only then we can achieve generalization. So my research focuses on the tail of this distribution. So when we don't necessarily know the names of these objects, we can use attributes as a side information. So attributes are visually discriminative properties of objects like blue crown, white belly, black eyes, and these are annotated on a class basis. So it's very costly to annotate attributes for every image, of course. And depending on whether the data set that we are annotating is fine-grained or not, which means if it contains objects that are visually very similar with each other, like different species of birds, then we need many more attributes, and annotating them on an image basis is very expensive. So it doesn't really solve the labeling data problem. But instead, we can annotate attributes on a class basis, which requires asking a field expert to give us the attribute names of these objects that they are familiar with. And then, and some of these attributes are common, we need to build vectorial representations of these attributes. And some of these attributes are in this case, the first attribute is only specific to the first class. So we take the value of 1 for the first class and 0 for the other class. And then some of these attributes are common. So the vector will have the same value for this attribute. And then some of these attributes are relative to each other. So we can also have values between 0 and 1. And this way, instead of representing a class as one hot vector with one depending on where in the vocabulary of all the classes this class appears, and which, by the way, also assumes equal distance between different classes, which is problematic. We can build more discriminative space where similar classes are embedded close to each other and different classes are embedded far away from each other. So we build this vector space. And then for many different multimodal learning tasks, we can use such a simple multimodal embedding framework where we embed the visual data, in this case images, into the image feature space. And this space can be learned with a deep neural network like ResNet. And we freeze this space. And then we embed labels, class labels, into the attribute space. And this space is learned with, this is a vector space, how I described before. So depending on how much of black appears in zebra, it will have a higher value of black and so on. And we fix this space as well. And then the next step is to find the compatibility between these two spaces. So we have image features available, we have class attribute labels available, and these are given. So the W's are the parameters that we learn. And this could be a linear function. So that determines the following. All the images that belongs to the same class, when they are projected onto that space using W, are going to be embedded close to each other and far away from the other classes. If we have managed to learn such a projection function, then at test time, if we receive an image that from a completely different class that we have never seen before, we can extract image features from it, and then project it onto the attribute space and search for the nearest attribute vector among the seen or unseen classes. So we can say the closest attribute vector belongs to this class, so this unknown image must have that label. So this is how we do classification. And particularly this, the task of zero-shot learning is interesting in these cases because basically we learn the this projection function using images of some classes. And then at test time, we will have completely unseen classes. But imagine that if we allow in this search space all of the classes, like both the classes of objects from which we have seen examples and completely unseen objects. This is a very difficult problem because the images of seen classes have allowed us to explore the space of seen classes. But as the model has never seen any images of unseen classes, it hasn't properly explored that space. And mostly, in these cases, the model has a bias towards seen classes, so there are mistakes, many mistakes. So there are many benchmark data sets for zero-shot learning. For example, animals with attributes and birds data sets. This one contains 50 classes. All the images of 40 classes are used for training, and all the images of 10 classes are used for test. And we need 85 attributes. For birds data set, it's a much fine-grained data set. So with 150 classes for training and 50 for test, but all coming from different bird species. That's why we need many more attributes, because many of these attributes are common actually. And then, so generalized zero-shot learning means the search space at test time contains both seen and unseen classes, which is a more difficult problem. But we can compute the accuracy of images that come from unseen classes, from seen classes. This just computes the number of correctly classified samples in a class divided by the total number of samples in that class. And then this is summed up for all the classes, and we divide by the number of classes. Because if our data set is imbalanced, some classes are going to dominate the results if we don't do this averaging. If, for example, we see a lot of different cars, and if we compute the accuracy without dividing by the number of car images, then if the classifier predicts cars more often, more correctly, then the accuracy will be higher. But this is wrong because we need a generalizable classifier. And then the harmonic mean is just the harmonic mean between these two accuracies. We look at the harmonic mean results because we would like both the seen and unseen class accuracy to be high, ideally. So this line shows results with learning with class labels, which is like a ResNet. And we trained it with 150 classes of birds, the images, and then we tested it on, in this case, 50 classes of birds, in this case, 150 classes of birds. And unseen class accuracy is 0 because the vocabulary doesn't contain unseen classes. It's impossible to predict unseen classes in this case. With multimodal embeddings framework, learning with attributes, we obtain a low unseen class accuracy. The seen class accuracy drops. We have a positive harmonic mean. But of course, we need attributes to be able to do that. And also, these two accuracies are still very, very far, very different from each other. So there are many different techniques proposed to bridge these gaps, to improve these issues. One of the most prominent ones of these solutions is data augmentation using generative models. So we have attributes which are class discriminative. We can use them as a conditioning variable in a generative model to generate features of unseen classes. This way we can train ResNet models with that and improve results. I'm not going to get into that because I talked about it last time. What I would like to talk about is the one prominent problem with attributes, which is some of these attributes can be incidentally correlated. And the model oftentimes doesn't have any way to recover from it. Because, for example, always the model, when it saw a yellow throat, maybe it also saw a yellow belly, and it learned that yellow throats always occur together with yellow belly, and vice versa, maybe black throats always occurred with black bellies. And now, instead of learning in the meaning of individual attributes, models learn combination of the attributes, and then when at test time it receives a completely different class, an image from a completely different class, it is not able to disentangle these properties. So how can we tackle this? This work was presented at NeurIPS last year. What we did was we take an image feature, we take an image, we extract image features from it. This is like an intermediate feature. This can be like a ResNet. And then from there, we try to learn groups of attributes that are grouped into body parts. We have done this grouping manually. We said all the belly attributes will be grouped together, all the breast, in case of birds, grouped together, and so on. And we have a group, I think in total 25 groups like this, which means we learn 25 prototypes here. And then these prototypes will be kind of converted to attention maps that can be overlaid onto the image, and this way we can optimize where the model looks at while it is predicting these attributes. And if it is looking at a wrong body part, then it's going to be optimized. And we predict attribute values from that. We take the maximum value in this attention map and say that for that particular attribute group, this image contains this much of value. And then because we have access to ground truth attribute vectors, we can backpropagate, we can compute the distance between the ground truth and the predicted attributes and backpropagate this loss back through the network. And then we can, another, I'm not sure if I will talk about it, but another aspect of the model was that we combined it with the multimodal embeddings framework so that it also learns a better projection function, but a linear projection function, exactly the way I described before, together with this regression loss. And so this way, if we use only the multimodal embeddings without doing this attribute prototype learning, then these are the results on this particular image for the breast, belly, back, and so on attributes. Those are the attention maps. And we can see that both the attention maps are very wide, and also they don't necessarily point to the correct body part. But by doing this prototype-based learning, we improve the localization of the attributes. Another interesting example was to see, or another interesting test was to see whether for the same exact attribute value or attribute type, what would be the visualization of the attention maps. In some cases, like zebra, tiger, and zebra, this attribute is present, and the model is able to localize the stripes attribute. But for rat and for killer whale, these attributes, although they are not present, it doesn't appear in the ground truth vector. The model has learned the meaning of the stripes attribute and points to the stripes on the image. That was an interesting kind of surprise result that we saw. Coming back to the goal that we had. So these were the results that I showed with multimodal embeddings using attributes. We had such a low harmonic mean and a big gap between the unseen and seen classes. So when we use images to improve the attribute values, we have seen a huge improvement actually. using these, so learning better image features using the using the attributes as a guidance worked very well. As a conclusion, attributes are actually compositional. They make up an object. So if you want to know whether the model has looked at the correct parts or has predicted the correct properties of objects before making a decision, attributes is a really good means for determining these things. And then they are a means for transferring knowledge from seen to unseen classes. We have seen for the zero-shot learning problem, it's an effective source of side information when we don't have access to images. And then we also can explain decisions of the classifiers by localizing and referring to the discriminative attributes. So they become important for explainability purposes too. Instead of just predicting that this object is a black-footed albatross, if I tell you that this object contains, or if the model tells you that this image contains black feet and black plumage, then you're going to be able to maybe trust the model better. Okay. So I will now talk about modeling the theory of mind via conversations with attributes. And what I mean by that is if I want to provide different type of descriptions or explanations to the user depending on the requirements of the user, then I have built a theory of the user's mind. Which is important, and this is something that we always do while we are communicating with each other. For example, if I talk to a 5-year-old and if I'm trying to explain them what is an attribute, I will use different words than if I'm explaining a graduate student what is attributes. So we would like the machines to have the same capability of empathy, so to say. So of course, this is a huge topic, and we are not able to solve this task of making better conversations and keeping in mind of the user, of the communication partner's abilities. We have designed a task that can be used in simulations. So in this task, we call it image reference games. We show 2 example images from 2 different classes to one neural network, and actually to 2 neural networks. And we would like the first neural network to randomly pick one of these images and describe it to the second one. And of course, and the means for communication is language, and the simplest language is attributes. So they communicate using attribute names. And so the first one describes the image it picked. The first one, it says red, and the second one is not able to see or pick the correct image. And because the second agent is colorblind. So whenever a color attribute is presented to the second agent, it's not able to pick correctly. And so they play this game together many times. And the first one observes the behaviors of the second one and forms a mental model of the second one and thinks, okay, if I mention color attributes, the guy is not able to pick correctly. So I should try another type of attribute, also discriminative, but maybe not the most discriminative, which could be the shape property. So it says round, and the second one is able to pick the correct image now. How do we achieve that? We have a model with 2 components. One of them is a speaker, the speaker agent. The second one is a listener. And in this example, the listener is colorblind, but it could be any disability. And the nice part is, I mean, this doesn't have to be, but the simplifying factor is both of these agents have the exact same, so they see the same images and they have the exact same image processing part. So the perception is the same. They use the same neural networks. And then they have to, there is another step of multimodal embeddings. They have to predict which attributes are present. Something here might be different. So this attribute prediction can be done differently. So after predicting the attributes for both of the cases, the first one subtracts these two attributes and sees the red beak is the most discriminative attribute. Of course, first in the very beginning of the game, it is going to propose the red beak attribute. And then the second one, because it is colorblind, there is some noise added to the predictions of the model. It's not going to be able to pick the correct image. And this reward of -1 is going to be communicated to the first agent, to the speaker agent, such that it updates its own agent embedding about the second agent. So this is maybe the theory of mind component. It keeps track of the history of the answers. And then once the correct label or correct attribute is communicated, then this attribute leads to the correct prediction for the second agent, and the reward is +1, and then the agent embedding gets updated. So we see that with more and more gameplays, the speaker agent converges and also is able to serve to multiple different disabilities at the same time. So these are some qualitative examples. For the first game, the most discriminative properties are these at the top. The chosen attributes are in the second, and this is the gameplay. So these two images are presented. The first one was selecting this image, but because the described attribute is color related and this agent is colorblind, the prediction is wrong. With more games, the first agent learns to talk about patterns or shapes more and more often, and this way the second agent is able to pick the correct image. And with 100 game, all of the games have converged, and always, although the most discriminative attribute is colors, the first agent, the speaker, talks about shape-related properties. So another way of using communication for classification and for explanation is this work that we actually are going to present on Friday. CVPR, this Computer Vision and Pattern Recognition Conference, is going on at the moment. It's in the afternoons, actually, because it always happens in the US, but remotely this year. So what this game is about is slightly different from the previous game. This time, only one of the agents has access to the image. It looks at the image, but we restrict its speaking capability. So it is not able to say, it's not able to answer questions that are about classes, but it can only answer questions that are about attributes. So the first agent has some prediction of what are the possible classes that could this image show, and but he can't decide which one because he doesn't have enough information. So it asks, is it furry? And the second one says yes, looking at the image. And then the first one this way can eliminate two of the classes already. And then the next question is, does it have whiskers? This way it eliminates one of the classes again and concludes that it's a dog. So this way of communicating, this way of forcing the second agent, the decision maker, to reveal its own decision process makes the decision-making process more interpretable as well. And as a byproduct, we have a decision tree on the one side. So this framework is also composed of two components. One is recurrent decision tree agent. This is essentially an LSTM and then a multi-layer perceptron attached to it. This LSTM keeps track of the gameplay of which classes are available and which classes have been eliminated. And the MLP just is responsible for picking the next question. So in this example, the next question, the one that gives the highest score, is Whiskers. And the second agent is an attribute-based learner. This agent is capable of answering any question about this image. It has a very deep network that is trained on images, on very large-scale images. And on top of it, there is an MLP. This is just to, it's like a multimodal embeddings framework, basically, to be able to predict the presence or absence of every attribute that could appear in this data set. And in fact, for all of the attributes, this framework is able to answer every question, but it is not allowed to communicate all the answers all at once. It can only communicate the answer that of the question that it is asked. In this case, it is Whiskers, and then the answer helps the first agent to communicate, to update its own mental model, and also eliminates the remaining classes. In this case, the game has converged. No answer was a useful one. So in which cases would this kind of a framework would be helpful? Let's say we have presented two images to this kind of a decision tree-based decision maker, and we asked whether these images have white underparts. According to the answer of this question, both of them were yes, and then the two images were classified into the same or the equivalently into similar categories. And then there were many more questions asked about it, like the breast patterns or black beak, and all the time all the answers were correct and the same. At the end, one of the answers is different. For black wings, the first image doesn't contain black wings, the second image does. Although these two images belong to the same class, there is a mistake in this case. The first image was classified incorrectly, but we can see that indeed the black wings are not visible because the bird is flying. So this was categorized as this class, and this was correctly classified as this class. So we can look at what the decision maker has done in the course of the decision making process. And also we can look at the cases where, for example, again, these two images belong to the same class, but as you can see, they look quite different. And this is because one of them is a male bird and the other one is female. And in this case, they actually look very different from each other. Maybe in this case, the black crown is not really the most discriminative property for that species, but for particular images. So in this case, again, black crown caused a misclassification. So attributes as explanations. Oh, this I already talked about, sorry. But this is another kind of confirmation. I will pass. So compositional zero-shot learning and audio-visual recognition. This part is much shorter because, like I said, this is a task that I got interested very recently, and I would like to kind of present it to you because also it's a relatively new task. There aren't so many papers that came out in this domain. So what is compositional zero-shot learning? We have images on one side, we have their labels on the other side, but the image labels are not the label of the class only, but this label contains the state of the object. And in fact, if we look at, for example, dry dogs and wet dogs, they actually look very different from each other. We are able to understand that these are dogs, both of them are dogs, but although they look very different. And so maybe dryness or wetness property affects a dog and a cat the same way because they both have, they are both furry. But the wetness property or dryness property affects the car in a much different way. So when we say this is a wet dog and versus this is a wet car, this property doesn't affect these two objects the same way. So their visual appearance changes significantly. And so we have access to, in this task, we have access to images and their compositional labels for some compositional labels. For some compositional labels, we don't have any images available. We have seen dogs, cats, cars. So we have seen all of the examples from all of the classes, and we have seen examples from all of the states, all of the attributes, but we haven't seen this particular combination before. On the other side, we have, of course, the meaning, the semantic meaning of these properties, no matter how the visual information looks like. From the meaning of the word, we can also build a representation of what is cute, what is old, and how do they relate to these classes. And the aim is to find a compositional space where visually similar and semantically similar objects are embedded close to each other, and visually and semantically different classes are embedded far away from each other. So one kind of solution or one proposed solution that we have worked on was to define a graph that connects the nodes or that defines the objects and the primitives within a graph structure, and then the combinations of these nouns and states are learned depending on how semantically similar they are. And this can be also cast as a graph neural network, where the learning of the weights between different nodes is also affected by the visual appearance of the objects. And then the next step, of course, once the GCN has converged, we have an output graph. Now the different kind of the similarities between different classes and different states have been fixed. Now we can use this graph as like a side information, the way we were using attributes before. So we project images onto that space, and we project this graph values onto that space, and we learn that these, for example, cute cat appears here, cute dog appears here. They are close to each other because they are both visually similar objects, and then old car is far away from them, which is also normal because car looks very different. And then old dog must be around here, close to the car and close to the dog. This is the aim. So there are mainly two data sets that are used to evaluate these compositional zero-shot learning tasks. And these data sets contain images, still images, and their compositional labels. So this graph neural network-based model is predicting this noun or this state object composition as the first one. This is the second one, this is the third one, and this is the correct one. So mostly in the MIT states case, these examples are correct. There are some interesting incorrect results. The correct noun, the state object pair was wet cat, and it is predicted as a tiny animal, which could also be true for this case. And then UT Zappos is a data set with shoes, and it's a bit sometimes ambiguous because the material of the shoe is not really very easily recognizable or something. And also these two data sets are not as large as ImageNet, for example. So we have also proposed in this paper an alternative data set which is much larger scale, and we also ensured that the split between seen and unseen classes is really completely disjoint. Yeah. So another interesting task in this domain is open world compositional zero-shot learning. So this is actually also a rather interesting phenomenon, because during training, our model has access to scene compositions. So we have images and their corresponding labels that are used to train this model. And then we have, the model has no access to the images of the unseen compositions. In fact, at test time, it doesn't even know what is a seen, what is an unseen composition. And then it is also plausible or possible to, of course, to think that some of these attribute or state object compositions actually are implausible to appear, such as ripe dog. So there will not ever be an image that shows a ripe dog, because this doesn't exist. So the model has no capacity to determine that a composition is unseen versus unfeasible. So in this setting, we have defined these unfeasible compositions, and we want the model to be able to predict whether a composition is unseen or unfeasible. This is the most general sense of this task, basically. The whole zero-shot learning is also kind of, this is the ultimate goal. So what we do is, so we have a multimodal embedding framework. We take the representations from the states, from the objects, and then from the image. We embed with a composition embedding onto the same space. This could be a GCN. It doesn't really matter, whatever works. And then the next step is to predict which compositions are feasible and which are unfeasible. And for that, we have another neural network. And what we do is, actually, it's a clever, simple trick. We say that if two objects are visually similar to each other, they must share states. And if two objects are visually very different from each other, we don't know whether they share this state. So, for example, a tomato and an apple looks very similar. So all the properties of tomato should be inheritable for the apple. But a dog and a tomato is very different. So we don't know whether all the properties of tomato can apply to dog. In this case, ripe doesn't, for example. And then based on these feasibility scores, we adjust the margin, or we adjust the possibility or the available vocabulary for prediction. And this can be done in a soft manner using this adjusting the margins, or or a hard masking manner where we completely ignore. We say these properties are not feasible, so I'm not going to include it in my vocabulary of predictions. Okay, and some qualitative examples. All of these, I think, are on the MIT States dataset, and the first model doesn't use these margin adjustment. The second one does, and we see that the first results are always incorrect, or in some of the cases they are not even infeasible, such as unripe boulder. And then this margin adjustment based on the feasibility scores improves the results significantly. Yeah. Okay. Very briefly, audiovisual knowledge, how to distill audiovisual knowledge. This has a lot of compositionality components as well. That's why I decided to add this in my talk. So what we want to do is we have access to a lot of a large-scale image data set like ImageNet, and we have learned a deep neural network like ResNet using those images. And if we extract individual images from a video, we can process it easily. And then some of the videos also, I mean, a lot of the videos actually contain audio information. And we make use of the audio information when we want to predict classes, predict which class this video belongs to. And so we have an audio teacher, an image teacher, and a video student. This is a much weaker network because also video networks require a lot more computational requirements, and we want to keep this simple. We want this network not to be computationally very demanding, but we want it to use the information that comes from pre-trained image teachers and audio teachers and make use of that information to predict the label of that video. So like I mentioned, a little bit more details on the framework. We have, have I run out of time? No, I have 5 more minutes, right?
Yes, Zeynep Hocam, you have about like 7 minutes, but considering the question, maybe 5 more minutes.
Okay, good. Okay, so yeah, so a little bit more details about the framework is we have a 2D network for an image teacher. This is, like I mentioned, frozen. It's learned before. And then the audio teacher is also frozen. This means we are not really using a lot of compute power to do the classification task. And then the 3D video student is a tiny network that makes use of the knowledge learned by the image teacher and the audio teacher. We show results that indicate learning this compositional, this contrastive learning framework is very useful for training small networks for bigger tasks very shortly. And some visual results. For the playing cello class, these are the properties that are predicted. For typing, also these are the attributes, or these are the predictions. And in this case, the A is where the visual information and the audio information are really kind of following each other. Whereas in this case, writing on board, maybe the audio could be different. It is not only about writing action, but maybe there is background noise. And then in this case, it is totally separated. While applying the lipstick, these are YouTube videos. Either there is background noise like music, or the person is explaining what she is doing, but the sound has nothing to do with the action. Yeah. Okay. As a conclusion, we combine and recombine smaller parts into a meaningful whole, and this way, so this we call compositionality, and it is important to boost generalization. This is also reduces sample complexity, and it improves interpretability. Instead of just predicting that this is a dog, if we predict that this is a wet dog, then it gives more information about the capabilities of the model. As a summary, I talked about attributes and language-based explanations with the lack of visual data problem. And then I mentioned that vision and language complement each other. Language in this case was attributes, but we can extend it to natural language. In fact, some of these works are focusing on natural language, so if you're interested. And developing explainable deep models is important for user acceptance. So there are many different ways of achieving explainability. One of them is improving the predictions of the model, making it transparent. Another one is outputting the intermediate decisions so that we can see afterwards if the model is behaving as expected. And in general, why are we interested in explainable artificial intelligence? In a case where, let's say we are sitting in a self-driving car, the car is moving forward and we have decided to go to sleep, nothing special is happening, and the next time when we wake up, the car has stopped. As a user, we would ask what happened, and then the model would say, I was driving down an empty road, I decided to slow down as a ball appeared on the right, I saw a child running towards the ball, so I decided to stop. This and maybe including the replay of what happened actually. So this kind of an communicative car would be also much more trustable than a device which we don't really have any idea why they come to a certain conclusion. And then when it comes to language-based explanations, the user might ask alternative scenarios like what would have happened if you did not stop. Then the model should be able to say if there was an impact, the child would have gotten hurt. Of course, answering such a simple question requires a lot of complicated processing, and we are incapable of doing that yet. So why is it so difficult? Because the model has to imagine alternative scenarios that hasn't happened, and imagine what the consequences would be. So develop some form of empathy and be able to handle uncertainties at the same time. And also the language has some intricacies, like the child would have gotten hurt but not broken. So the choice of words is also very important. With that, I thank you for your attention. I'm done with my talk.
Thank you very much, Zeynep Hocam, for your presentation. So for the interest of time, we have two questions on our Q&A window. So maybe the first one is quite long. So do you mind reading and answering? And I can say answer live so the other participants can read it as well.
Okay.
Should I read it by Mehmet Burak Sayıcı. I think we don't need to read it out loud.
Okay. Yeah. Yeah. This is a very good question. So the question is about how to measure whether the attention map is really covering the area that it is supposed to cover, or it is covering random things. So this is an unsolved problem, so I don't have a very good answer for it. But one task that people usually evaluate these attention models with is like weakly supervised object localization, or object localization in general. If the span of the attention map is within the object, then and not the background, then it is considered as a good attention map. But of course, if we are interested in explainability, this means the whole extent of the object is not the most important, it doesn't necessarily contain the information that is required to make a decision. It contains extra information that we don't need for the classification. So, for example, if the shape of the beak is important for that class, then pointing to an attention map spanning the entire object and looking at the tail doesn't really help. So in these cases, there are pointing games. I don't have the paper in mind, but check internet for pointing games for explainability evaluation. So we are essentially interested in the minimum required region that is necessary for doing the classification. So if you remove any part of the attention, then the model shouldn't be able to make the decision correctly. And we also require the attention map not to look outside of the image, outside of the object. So it needs to be as comprehensive as possible.
Thank you very much for your answer, Zeynep Hocam. There was a brief question, if we have time, maybe within a minute. So it's a question about page 28, and Arif Chechen is basically asking, whale and humans are both mammals, but they don't look the same. So how much these models can kind of like take a concept of being a mammal into a consideration?
So this is like a superset. We are, I mean, so we would like to explain the classification decision for a like a, if you want to explain what is a mammal, then pointing to, I mean, it's not clear where to point on the image, because this is not really an interesting decision to make in the first place. But we are interested in explaining much more fine-grained properties. For example, if I want to explain what is a car versus a bottle, if I just point to the entire extent of the car and then say, okay, this attention map or this segmentation mask looks like a car, and this segmentation map looks like a bottle, it's a valid explanation, but not a useful one. So instead, I would prefer to build explanations where it really is important to point to these fine-grained differences between objects. So in some cases, it's not really meaningful to even build a model to achieve that task. In the context of explainability, I think saying that a human and a mammal look so different, so they can't belong to the same class, doesn't really, I don't know, not really useful in my opinion.
So thank you very much Zeynep Hocam, and teşekkürler in Turkish. So we are